Hello everyone, my name is Leza Malik and I am presenting my work for the seminar on generative artificial intelligence. Today, I'm going to walk you through my scoping literature review, which explores the role of large language models in sign language approaches. Over the next few minutes, we will look at how AI is completely changing how we translate and generate sign language. But more importantly, we will discuss why having great technical accuracy in a lab doesn't always mean that the technology is actually useful or accessible for the people who need it. To truly understand where the state of art is today, we first have to look at what researchers were struggling with a few years ago. Historically, AI models treated sign language in a very rigid way. They tried to force a highly expensive 3D spatial language into flat, one-dimensional text sequence. In the literature, this intermediate text step is called a gloss. If you look at the diagram on the screen, you can see this exact pipeline. The AI takes a video, forces it into these uppercase gloss words, and then tries to translate that into a spoken language sentence. So this created a massive bottleneck. And why is that so? So because creating these glosses relies entirely on human experts manually annotating hours and hours of video data, it is incredibly expensive and time consuming. As a result, AI models were only being built for a few well-funded sign languages, while the vast majority of the world's sign languages were completely ignored. Thankfully, the introduction of LLM sparked a massive generative shift in the field. The new LLM pipeline completely bypasses that restrictive gloss bridge. Instead of relying on the manual text labels, modern architectures map native visual streams directly into the framework of a frozen LLM. As the diagram shows, the process now usually starts with a multimodal encoder that extracts visual features directly from the video input. A feature adapter then takes those visual cues and aligns them so that the language model can understand them. So the real magic happens in the reasoning core. By using a frozen LLM, the system taps into a massive amount of pre-trained world knowledge. This allows the AI to figure out the context of the sentence naturally and generate a fluid text or an avatar output without needing to hand label every single gesture. To evaluate how effective this shift actually is, I conducted a systematic scoping review. I based my methodology on the Prisma 2020 framework and used the spider search strategy to ensure my findings were rigorous. I specifically targeted literature published between 2019 and 2026 to capture this modern generative era. My focus was divided into three main areas: sign language translation, sign language production, and crucially, human-centered AI. This brings me to my first research question: which architectures are actually leading the field right now? To answer this, we have to look at translation and production separately. Starting with translation, which is turning the video into text. We are finally moving away from the rigid flat models. One framework that really stands out is SpaMo. If you look at the flowchart on the slide, you can see how it splits the video into two distinct streams, one for the spatial shape of the hands and one for the temporal motion. This is a massive leap forward because it perfectly mirrors the actual linguistics of how humans sign. Another major breakthrough I found is the LSLM framework. Instead of looking at 2D pixels, it maps signs directly onto a 3D body model. This is crucial because it makes the AI robust against bad lighting, cluttered backgrounds, and weird camera angles, which are exactly the messy conditions we see in the real world. On the other side, we have sign language production, which is generating a 3D signing avatar from text. Historically, early generative models really struggled here. They suffered from what we call spatiotemporal oversmoothing, where the AI would lazily blur transitional frames together, resulting in robotic, illegible movements. To solve this, a recent framework called SignLLM has been incredibly innovative. As you can see in the image, it outputs a skeleton pose video based on the text prompts. But what makes SignLLM truly special is its use of reinforcement learning. Instead of just mathematically plotting points on a grid, it actively rewards the system for creating avatar movements that are biomechanically plausible. It's finally making these avatars look human. For my second research question, I looked at how these models perform on the standard benchmarks. The chart here shows the performance on the widely used Phoenix 14T dataset. You can see that the SpaMo leads the pack, setting a bar high with a BLUE4 score of 24.32. This proves that the gloss-free LLM-based architectures easily beat the older baseline models. However, we have to look at these models critically. I call this the metric illusion. The problem is that the BLUE4 metric was designed for spoken language text, so it only measures semantic word overlap. It fundamentally ignores the grammatical well-formedness and visual syntax of sign language. So while an AI might score very well on the paper, its actual real-world translation might still be incredibly confusing for a deaf user. The exact problem leads into my third research question, which evaluates these systems through the lens of human-centered AI. The most glaring issue I found in current models is the affective consistency gap. In sign language, facial expressions are not just for showing emotion, they are a mandatory part of the grammar. Take a look at the image. The avatar on the top has a neutral face. If it signs a sentence with a neutral face, it's just a statement. But if the avatar raises its eyebrows, as seen in the bottom prompts, it changes the grammar of the sentence into a yes-no question, like do you commute to work by bike? If an AI generates perfect hand shapes but gives the avatar a blank robotic face, it is a grammatical failure. This lack of consistency pushes the avatars into the uncanny valley, which makes them uncomfortable to watch and heavily damages their credibility with the users. The second major human-centered AI issue is a physical accessibility barrier. Right now, the AI industry is dealing with severe computational gatekeeping. The state-of-the-art models we just discussed require massive GPU memory to run simply because models are so heavy. However, deaf and hard of hearing users don't carry supercomputers around with them. They rely on mobile phones and wearable devices for daily assistance. As you can see in the synthesis table on the screen, the literature shows we have created great generative solutions for the gloss bottleneck and the biomechanical realism. However, the problem of edge deployment, which is making these large LLMs actually feasible on a mobile device, remains a massive open challenge. Before I wrap up, I want to highlight a very critical limitation I observed across all of this literature. There is a massive geographical and cultural imbalance in the data. Right now, the vast majority of these state-of-art models are trained almost exclusively on American Sign Language and German Sign Language. That means roughly 295 other global sign languages are being completely ignored, creating a huge barrier to global equity in AI. Furthermore, the history of assistive tech is full of tools that are technically functional but culturally useless. I call this the vacuum effect. These generative models are almost always developed and tested by hearing engineers in isolated labs with zero direct participatory involvement from the deaf community themselves. We have to change how we build these tools. To conclude, my review highlights that while large language models have successfully pushed sign language AI past the gloss bottleneck, we still have a long way to go before these tools are genuinely useful in the real world. Looking towards the future, I have identified three main priorities for the researchers. First, we need to focus on model distillation. We have to build edge deployable architectures that can actually run on a smartphone. Number two, we must prioritize NMM-aware models. AI developers must treat facial expressions and non-manual markers as mandatory grammar rather than just an afterthought. And finally, the most important step is the participatory design. We have to stop building assistive technology in isolated labs. Moving forward, true innovation will only happen through direct co-creation and testing with the deaf and hard of hearing community. Here is the bibliography detailing the primary sources, including the Prisma guidelines, architecture frameworks, human-centered AI studies that inform this presentation. Thank you so much for your time and your attention. I would now be happy to open the floor to any questions that you might have.